Have you ever wondered why every time you throw something, a rock, a basketball, or even a cannonball, it seems to follow the same kind of path? It goes up, for a moment it slows down, and then it falls back down, tracing a smooth curve through the air. This is called projectile motion, and in the ideal case, when we ignore air resistance, that curve is called a parabola. Projectile motion happens when an object is launched and then moves under the action of gravity. In our case, the object is launched neither straight up nor perfectly horizontally. It is launched at an angle. We can represent its initial velocity, called v0, with an arrow. This arrow tells us two things: the direction in which the object is moving and how fast it is moving. In physics, an arrow like this is called a vector. And the useful thing about vectors is that we can split them into simpler parts. Using basic trigonometry, we can decompose the initial velocity into two components. One component is horizontal, and the other is vertical. We call them v0x and v0y. Now we can use the components of v0 to study the motion in each direction. In the horizontal direction, we have x of t equals v0 cosine alpha times t. So there is only one linear term controlling the value of x. In other words, along the x direction, the motion is uniform. The object keeps moving forward at a constant speed without accelerating. On the other hand, in the vertical direction, we have y of t equals v0 sine alpha times t minus 1/2 gt squared. Here, a second-order term appears. That term represents the effect of gravity caused by Earth's gravitational field. So vertically, the motion is accelerated downward, and when we combine the horizontal motion with the vertical motion, the full trajectory becomes a parabola. Mathematically, a parabola has the form y equals ax squared plus bx plus c. In this case, the coefficient of x squared is negative. That means the parabola opens downward. So the real motion is not one mysterious curve. It is the combination of two simpler motions, one horizontal and one vertical. Now that we understand the basic idea, let's go a little deeper. We can ask three natural questions. When does the object reach its maximum height? When does it hit the ground? And how far does it travel horizontally? The nice thing is, each answer comes from a simple formula. For the first question, we use the formula for the vertical velocity. Vy of t equals v0 sine alpha minus gt. This formula tells us how the vertical velocity changes with time. When the object reaches its maximum height, for a brief moment, its vertical velocity becomes zero. After that, gravity makes it start falling back down. So we impose the condition, Vy of t equals 0. By solving this equation, we obtain the time needed to reach the maximum height, Tmax equals v0 sine alpha divided by g. This formula tells us that the time to reach the highest point depends mainly on the initial speed, the launch angle, and the acceleration due to gravity. We can use a similar path for the second question, but this time, instead of using Vy of t, we use directly y of t. Our goal is to find when the object hits the ground. So, in our representation, the final height must be 0. In other words, y of t final equals 0. Again, we impose this condition, and in this case, we obtain two solutions. The first one is t equals 0. This simply represents the initial instant of the motion, when the object is about to be launched. The second solution is the one we are actually looking for. It gives us the time at which the object comes back to the ground, and we can see that this value is exactly twice Tmax. This also makes sense from the usual solution of a second-degree equation. One solution represents the beginning of the motion, and the other one represents the end. For the last question, we have to find how far the object travels horizontally. This distance is called the range, and it is pretty simple to calculate. We use the formula for the horizontal position, x of t equals v0 cosine alpha times t. Then we substitute t with t final using the formula we already obtained. This is because the range corresponds exactly to x of t final. So we obtain r equals 2v0 squared sine alpha cosine alpha divided by g. Now, to simplify it further, we use a trigonometric identity. Sine of 2 alpha equals 2 sine alpha cosine alpha. So we obtain the final formula for the range. R equals v0 squared sine of 2 alpha divided by g. We can observe that the range depends on twice the angle. And this is very interesting. If we study the function sine of 2 alpha between 0 and pi over 2, which corresponds to angles between 0 and 90 degrees, we see that its maximum value is 1. This happens when alpha is equal to pi over 4, or 45 degrees. So, in the ideal case, if we want to maximize the range of an object, 45 degrees is the best launch angle. And with that, we have reached the end of the video. Today we have seen an introduction to projectile motion followed by a simple analysis of its behavior. Of course, always remember that real cases can be more complex. For example, throughout this video, we assume that the object starts its motion from the origin of the axis. Obviously, this is not always true. But the goal for today was to introduce the concept in the simplest way possible. If you enjoyed this content and want to see more, consider subscribing to the channel and leaving a like. Thank you for watching, and I'll see you in the next one.